Okay. So good afternoon all, right? Okay, good evening. Okay. So let me know whether audio and video everything clear. So if it is not clear, please give some comment in chat box, right? Okay, so I hope everything is clear, right? Okay. So we are dealing with the subject electromagnetics, and in electromagnetics we have started the topic that is time varying fields, right? So in time varying fields we have started with Faraday's law. Right? Okay. So in Faraday's law we have seen that whenever there is a change in magnetic flux, so there induces an EMF around the closed loop, and here this minus sign is because of Lenz's law, right? Okay. Next we have seen we have written the Faraday's law in terms of what? In terms of electric field. So that is the EMF induced around any closed loop, you can write it as what? The circulation of electric field around any closed loop. So that is equal to what? That is equal to, I can write this as a minus dou by dou t into double integral b bar dot what? B bar dot dA bar. Understood? Okay. Or the same thing I can write in this manner, that is minus double integral dou b bar by dou t dot what? Dot dA bar. So this is the integral form here. This is the integral form of Faraday's law. So next we have derived the point form or differential form here. So that is curl of E bar is equal to what? Is equal to minus dou b by dou t, minus dou b bar by dou t. So this is the point form or differential form of Faraday's law. So this is the integral form, and this is the point form or differential form, and so this is the basic expression we have written for Faraday's law. From here we have written the integral form, and from this integral form we derived this point form or differential form, right? Okay. Okay. So here I said that since circulation of electric field around any closed loop is not equal to 0, and hence here this electric field is what here? The electric field is non-conservative. So that's what I have told here, right? Okay. So the electric field is nothing but non-conservative, right? See, what do you mean by circulation of electric field around any closed loop here? What do you mean by this? See, I have already told that E can be written as what? F bar by what? F bar by Q. So F bar dot dl bar will represent what? Will represent work done, right? So by Q will represent what? Work done per unit charge. So work done per unit charge around any closed loop. So work done per unit charge is nothing but what? Potential. So this represents the potential around any closed loop. Understood? Okay. Okay. So here it is non-conservative field here. So since here curl of E bar is not equal to 0, so this E bar is nothing but what? Is nothing but non-conservative field. Right? Okay. Okay. So these things we have seen. So I have shown you the difference. I have shown you the showed you the difference, how to deal with what happens in case of static fields, and what happens in case of non-conservative fields, right? Okay. So in the previous session I have taken one example. So that is, I have considered here R1, and here, so here I have considered 1 volt, and here I have considered R2, right? Okay. So R2 I have considered some 9 ohm, R1 I have considered some 1 ohm. Okay. So here I have calculated VAB, yes or no? I have calculated VAB by moving in clockwise direction and also by moving in anti-clockwise direction. So in both the cases here, we got VAB, the same value, whether in clockwise direction or in anti-clockwise direction. So VAB, we got what here? We got the same voltage, yes or no? Okay. So what we got here, actually the current that is flowing here is 1 by 9 plus 1, that is 0.1 amperes. So here we got 0.9 volts, yes or no? From here to here we got what here? 0.9 volts. So from here to here in anti-clockwise also we got what? We got 0.9 volts, right? So this is what we got, I guess, right? Okay. So Y means here I is equal to what? I in this loop is nothing but 1 by R1 plus R2. So that is 1 by 10, that is 0.1 amperes, right? So here 0.1 amperes is flowing like this, 0.1 amperes. So you will get here 0.9 volts, and on this side also you are going to get 0.9 volts from A to B. So whether you move in clockwise direction or anti-clockwise direction, you will end up with what? You will end up with the same result. So that means here it is not depending upon what? Potential means what here? The work done in moving the unit charge from A to B. Understood? So whether you move in clockwise direction or you move in anti-clockwise direction, in both the cases we got the same work done per unit charge. Yes or no? Okay. Why here? Because here the field is nothing but what here? The field is nothing but what? Is nothing but conservative field. So here whatever the electric field that we are going to have, that field is nothing but what? That field is nothing but conservative field. So here this is valid here, that is the circulation of E bar dot dl is equal to 0. So which we are calling it as KVL, right? So this is valid here, right? So whenever we are dealing with a non-conservative field here, so that is we have removed this 1 volt source, right? So we have considered simply here R1 is equal to 1 ohm, and here we have considered R2 is equal to what? 9 ohm. Now I am removing this 1 volt source, so I am just completing the circuit in this manner. Now here I am considering A and here I am considering B. So here we have considered the magnetic field here. We have considered a time varying magnetic field. Yes or no? We have considered a time varying magnetic field is pointing into the board. Understood? And this is nothing but what? This is nothing but time varying magnetic field. Okay. So I have given something like T into minus AZ cap or something like this. Yes or no? Okay. So that means this magnetic field is increasing with respect to time. So if it is increasing with respect to time and pointing into the board, so that means the magnetic flux is increasing. The magnetic flux is increasing into the board. So whenever the flux is increasing here, what must be the direction of the induced magnetic field here? The direction of the induced magnetic field must be opposite to what? Must be exactly opposite to the direction of the actual magnetic field. So actual magnetic field is pointing into the board, so the induced magnetic field must point out of the board. So in this case we have seen that the induced current in this case is going to flow in which direction here? The induced current is going to flow in anti-clockwise direction like this. Understood? Okay. Okay. So in this case we try to determine VAB by moving what? By moving in clockwise direction. Understood? By moving in clockwise direction. So here what we have done here? Here we have connected a voltmeter. Understood? So this is going to measure the potential difference across this R2. Understood? Okay. So that is from A to B. So you are moving in clockwise direction. Right. So similarly, we try to determine the potential difference by moving from where to where here? From A to B. In anti-clockwise direction. So then you have measured the potential. We have connected here voltmeter, right? We have connected here voltmeter to measure the potential between A and B in which direction here? In anti-clockwise direction. Understood? Okay. Okay. So what we got here? Here we got I induced. How much we got? So I think I induced we got 1 ampere or something like that, right? Okay. Okay. So I think we got I induced. We got I think 1 ampere something, right? So 1 ampere is flowing here. If 1 ampere is flowing here, so then V1 will read how much here? V1 is equal to what? Is equal to VAB in anti-clockwise direction. So we got this as what? We got this as 1 volt. Right? Okay. So next Next here I induced is flowing in this direction. Yes or no? I induced is equal to what? Is equal to 1 ampere. If it is flowing like this, so here we got in clockwise direction here. In clockwise direction, so the voltmeter reading V2 is equal to what? Is equal to VAB. What we got here? We got minus 9 volts, I think, right? Okay, so we got minus 9 volts, right? So that means in the previous case, the work done, that means the potential difference between A and B is depending upon what? Is not going to depend upon what? It is not depending upon the path you are choosing. But here it is depending upon what? It is depending upon the path you are choosing. So if you move in clockwise direction, you are getting what? You are getting minus 9 volts. That means the reading of this voltmeter V2 will be what? Will be minus 9 volts. And if you move in anti-clockwise direction like this, then the voltmeter reading for this one, that means here if you move in anti-clockwise direction, this reading will be what? This reading is showing as 1 volt. So that means here we have not connected, in this circuit we have not connected any battery. We have not connected any battery. Understood? But how we are generating this induced currents here? How you are generating this induced currents? How we are generating? Because there is a change in magnetic flux. So whenever there is a change in magnetic flux, it is going to induce an EMF. That induced EMF is going to drive the induced currents. Okay, so we have represented the direction of that induced current here, right? So thus we have determined the potential across R2, that is V2, and potential across R1, so that is V1. Okay, so what we got here 1 volt, and here we got minus 9 volts. So that means here what is the law we have applied here? That is Faraday's law. Yes or no? So what Faraday's law says? The circulation of electric field around any closed loop is equal to what? Is equal to minus dou phi b by minus dou phi b by dou t, minus dou phi b by dou t. So this represents what? Circulation of electric field around any closed loop. This represents what? This is nothing but voltage around any closed loop, or EMF induced around any closed loop. Understood? Okay, so EMF induced around any closed loop is not equal to 0. It is equivalent to what? It is equivalent to time rate of change of magnetic flux. Understood? Okay, so we have seen these differences here in the previous session, right? Okay. Okay, so next see here. So now in this session we will see in how many ways we can generate the voltage. Okay, so that's what we are going to see now. So now we know that this basic equation, that is induced EMF, is equal to what? Is equal to minus dou phi b by what? Dou phi b by dou t. Okay, so where phi b is nothing but what? Where phi b is nothing but magnetic flux. So I can write this as what here? Double integral b bar dot what? B bar dot dA bar. So this represents the magnetic flux. Understood? Okay, so see here. If I assume B bar is uniform, if I assume B bar is uniform with respect to space, or I can say B bar is independent of integration variables. Okay, integration variables. So here the differential area, you are considering differential area means it is going to have what? It is going to have two integration variables. Yes or no? Okay, so here you are integrating with respect to what? With respect to two integration variables. So if we assume B bar is uniform with respect to space, or I can simply say if B bar is independent of what? Independent of integration variables, so then I can take this B bar out of what? Out of this integration. Yes or no? Okay, so then in that case I can write phi b is equal to what? B bar dot what? B bar dot double integral dA bar. So this represents the total surface area, so I can represent simply this as B bar dot A bar. Understood? Okay, so therefore phi b is equal to what here? So expand this dot product here, what you are going to get? B into A into what? B into A into cos theta, where theta is the angle between what here? Theta is the angle between B vector and area vector. B vector and area vector. Understood? Okay. See, the direction of area vector must be always what? Must be always normal to the given surface. Understood? Okay. So you should not forget these basic things here, fundamental things you should never forget, right? Okay. Okay, so now I am just substituting this phi b is equal to BA cos theta in this expression, right? Okay, so therefore VEMF is equal to what? Is equal to so minus dou by dou t. So phi b I am representing as what here? BA cos theta. Okay, so this is nothing but what? This is nothing but flux. This is nothing but magnetic flux, phi b, right? Okay, so forget about this dou by dou t here. So this is nothing but magnetic flux. Yes or no? This is nothing but magnetic flux. So whenever this magnetic flux changes with respect to time, then only you are going to have what? Then only you are going to have an induced EMF. Understood? Okay, so in order to produce an induced EMF, or in order to produce this voltage, what we have to do? We have to vary this flux. We have to vary this magnetic flux with respect to what? With respect to time. See, if this magnetic flux is constant with respect to time, then dou by dou t of this term will become what? Will become 0. Yes or no? Okay, so phi b must be a function of what? Must be a function of time. So this magnetic flux must vary with respect to time. So then only we are going to have an EMF. Then only we can generate an EMF. Understood? Okay. Okay. So now, in how many ways we can vary this magnetic flux here? In how many ways we can vary this magnetic flux? See, we can vary this magnetic flux by varying what? By varying only B field. Yes or no? Or by varying what? By varying area of the loop. Right? Or by varying theta. Yes or no? So how many ways we can produce the magnetic? How many ways we can change the magnetic flux here? That is by varying B with respect to what? With respect to time. If B varies with respect to time, then what will happen? The magnetic flux will vary with respect to time. Or if area of the loop varies with respect to time, if area of the loop varies with respect to time, so then also this magnetic flux is going to change with respect to time. Now similarly, theta is nothing but what? Theta is nothing but the angle between what? Angle between B field and area vector. So if theta changes here, with respect to time, then also this magnetic flux is going to change with respect to time. Understood? Okay, so these are the different ways through which we can vary this magnetic flux with respect to time. So if you vary this magnetic flux with respect to time, then you can produce what? You can produce the EMF. Right? Okay. Okay. Now see here. So here I am writing the same expression in this manner here. See here. So VEMF is equal to minus of. Right? Okay. Now let us consider only B field is varying with respect to time. A and theta are constant with respect to time. Area of the loop here, A represents what? We have expanded this B bar dot A bar here. That means this represents magnitude of B, this represents magnitude of A multiplied by cos theta. So here A means the magnitude of area of the loop, right? Okay. Now let us consider B field is varying with respect to time, whereas area of the loop and theta is constant with respect to time. So let us assume A and theta are constant with respect to time and B field is varying with respect to time. So in that case what you are going to get here? So A cos theta, you are going to get A cos theta into what? Into dou B by dou T. So this is one way to produce what? To vary the magnetic flux and thus to produce what? To produce an EMF. Understood? Okay. Next, let us consider only area of the loop is varying with respect to time. B field and theta are constant with respect to time. Only area of the loop is varying with respect to time. So in that case, what you are going to get? Tell me. So only area of the loop is varying here. B and theta are constant. So in that case, you are going to get B cos theta into dou A by dou T, right? Okay. So here I am considering B field is varying with respect to time. Here area of the loop is varying with respect to time, right? Okay. Next, so I will. Okay, so next, if I vary theta here, let us consider I am varying only theta with respect to time, whereas B and A are constant. So in that case, what you are going to get here? B into A into what? B into A into dou by dou T into cos of what? Cos of theta of T. So theta now it is varying with respect to time. Right? Okay. So these are the different ways. Through which we can produce what? You can produce the EMF. One is what here? By varying B field with respect to time. Understood? Next, by varying area of the loop with respect to time. Then by varying theta with respect to time. So these are the different ways to produce what? To produce an EMF. Right? Okay. Okay. See here. Okay. So these are the different ways through which we can produce what? We can produce EMF. Right? Okay. Now we will see one by one here. So by varying B field with respect to time, if only B field is varying with respect to time, let us assume only B field is varying with respect to time, whereas A and theta are constants. So if A and theta are constants and only B field is varying with respect to time, so then what will happen here? This term will go to what? This term will go to 0, and this term will go to what? This term will go to 0. Yes or no? If I assume only B field is varying with respect to time and A and theta are constants, so then this term will go to what? This term will go to 0, and this term will go to what? This term will go to 0. Understood? Only this term will be present. Now suppose if let us assume only area of the loop is varying with respect to time, whereas B and theta are constant. So in that case what will happen here? This term will go to 0 and this term will also go to 0. Only this term will be remaining. Understood? Now let us consider only theta is varying with respect to time, whereas B and A are constant, whereas theta is varying with respect to time. So in that case what will happen here? So this term will go to 0, only this term will be present. Understood? Okay. Now you can have the combinations also here. If suppose both B field and theta are varying with respect to time. If suppose both B field as well as what? Theta are varying with respect to time, then you are going to have this term and this term. This term will become what? 0. Okay. Similarly, if only area of the loop and theta are varying with respect to time, so then these two terms will be present. This term will be 0. If suppose all the terms here like B field, area of the loop and theta all are varying with respect to time, let us assume, so then all the three terms will be present. Understood? Okay. So in this manner you have to determine what? In this manner you have to determine the induced EMF. Right? Okay. So these are the three ways to produce what here? To produce an EMF. So now we will see one by one here. Right? Okay. So this one here, Parasmun, that's what I am saying now. I have told, I think I have covered your point, right? Okay. If suppose B field, area of the loop and theta all are varying, then all the three terms will be present. Understood? I will explain here. Just now started now. So I will explain each and everything, right? You will understand definitely, right? Okay. See here. So here, So consider this first term here. So by varying B field here, how we are producing EMF here? How we are producing EMF? So by varying B field with respect to time, we are producing what? We are producing EMF. So this is one way of producing what? Of producing EMF. Understood? Okay. So this action of producing EMF is called as what here? Is called as a transformer action. Is called as what here? Is called as a transformer action, and the EMF you are going to produce here through this process, we call it as what here? We call it as transformer EMF. We call it as transformer EMF. Understood? Okay. So this action is called as transformer action, and the EMF that is generated by varying only B field with respect to time, we call that as what here? We call that as a transformer EMF. We call that as transformer EMF. Okay, so why we are calling it as transformer action and why we are calling it as transformer EMF? So that's what we are going to see now. See here, see here, if I consider a transformer here, right? Okay. Okay, so let us say here I am having an alternating voltage I have connected here. Okay, so here I am having a primary winding. So here I am considering a primary winding. Okay, primary winding, and here I am having secondary winding. Okay, so here I am connecting load here. Here I am connecting a load. Here I am connecting a load. Right? Okay. Okay. So here, here if you observe here, the voltage source that I have connected is nothing but what? Is nothing but some alternating voltage source. That means it is going to vary with respect to time. So that means the current it is going to produce, will also varies with respect to time. So here what will happen here? So this time varying current will flow through what? Will flow through this primary winding. Yes or no? It is going to flow through this primary winding like this. Okay, so the current will flow through this primary winding in this manner. Understood? Okay, so whenever the current is flowing here, through this primary winding, we know that it is going to produce what? It is going to produce a time varying magnetic field. Yes or no? So whenever a time varying current is flowing, through the winding, we know that it is going to produce what? It is going to produce it is going to produce a time varying magnetic field. Yes or no? Okay. Okay. So a time varying magnetic field. So let us assume here, so inside the solenoid here, whenever the current is flowing through this primary winding, it is going to produce what? It is going to produce a time varying magnetic field, Understood? Okay. Okay here. So now let us assume the magnetic field produced inside the solenoid is like this, Let us assume here, right? Okay, so now we know that the B field is going to form what here? The magnetic field lines are going to form what? Are going to form the loops, closed loops. So that means whatever the B field that is produced here, in the primary winding because of this current, so that B field will try to form what? Will try to form the loops. It is going to form the closed loop like this. Yes or no? Why here? Because the B field will be always what? Will always forms the closed loops like this. Understood? Okay. So now what is happening here? So this B field, whatever the B field that is produced in the primary winding, now it is getting linked with what? With the secondary winding. Understood? Okay. So the B field that is produced in the primary winding is getting linked up with what? With the secondary winding or with the secondary coil. Understood? Okay. So in this manner. Understood? Okay, so the B field which is produced in the primary winding is getting linked up with what here? Is getting linked up with the secondary winding or secondary coil. Okay, we know that here the current is varying with respect to time, and hence this B field is also going to vary with respect to time. Understood? So now if you observe in the secondary winding here, so these B field lines are penetrating through what? Are penetrating through this surface. Yes or no? Through this surface of what? Through the surface of the windings. Through the surface of the windings. So the number of magnetic field lines that are penetrating through this surface, we call it as what here? We call it as magnetic flux. Yes or no? Now here the number of field lines that are penetrating through this surface of the windings is going to change with respect to time. Yes or no? Because the current is varying here with respect to time, and hence the B field will also varies with respect to time. So if the B field varies with respect to time, then the number of field lines that are penetrating through the secondary winding will also varies with respect to time. Understood? So that means in the secondary winding there is a change in magnetic flux. There is a change in magnetic flux. So we know that whenever there is a change in magnetic flux here, whenever there is a change in magnetic flux, we know that there induces an EMF around the closed loop. Yes or no? Okay, so whenever there is a change in magnetic flux here, there induces an EMF around this closed loop. This is the closed loop. Yes or no? Okay. Okay, yeah. So whenever there is a change in magnetic flux, it induces an EMF around this closed loop, around this closed loop. So that EMF is going to induce the current in the secondary winding, and hence you are going to see some induced current here. You are going to see some induced current in the secondary winding. Understood? Okay, so here in the secondary winding you have not connected any battery, nothing. You have not connected any battery. So what is happening actually? So whatever the B field that is produced here, whatever the B field that is produced within the primary winding, that is linked up with the secondary winding, and since here the current is varying with respect to time, the B field that is penetrating through the or linked with the secondary coil is also varying with respect to time. So because of this there will be a change in magnetic flux in the secondary winding. So whenever there is a change in magnetic flux, we know that according to Faraday's law, it is going to induce an EMF around this closed loop. So that EMF is going to induce what? That EMF is going to induce the current. So and hence you are going to see an induced current in the secondary winding. In the secondary winding. Understood? Okay. So here what is varying here? How we are varying the flux here? How the flux is changing? Because the B field here, the B field that is linking with the secondary coil is changing with respect to time. Understood? So here EMF in the secondary coil is produced because of the change in magnetic flux. Because of the change in magnetic flux. So that change in magnetic flux is because of what? Is because of the time varying magnetic field. Because of the time varying magnetic field. Understood? Okay. So that means by varying the B field with respect to time, we have produced what? We have produced an induced EMF in the secondary coil. Understood? So that's why this action is called as what here? This action is called as transformer action, and the EMF produced by this action is called as what? Is called as transformer EMF. Is called as transformer EMF. Right? Okay. Okay. So this is one way to produce what? To produce the EMF. To produce the EMF. Okay. Next. What is another way here? What is another way? So that's what we are going to see now. So another way here, I have said that by varying what? By varying area of the loop with respect to time. By varying area of the loop with respect to time. Here B field and theta are constant. Here by varying area of the loop with respect to time, you can vary the magnetic flux. If you vary the magnetic flux in this manner, then also you are going to have what? You are going to have the EMF. You are going to have the EMF. Understood? So here I will tell you one example here. I will tell you one example how we can vary the area of the loop and all those things. Right? Okay. See here. See here. So here I am considering a bulb here. Let us consider a bulb here. So this is bulb here, right? Okay. Let us consider this is bulb. So here I am forming the loop here, right? Okay. So let us consider the magnetic field. Let us consider the magnetic field is pointing. This magnetic field is not changing with respect to time here. This is constant magnetic field, right? So this B field is constant with respect to time. It is not varying with respect to time. Understood? So here you are having a constant B field that is pointing into the board, right? Okay, now here now here I am considering a conductor here. I am considering a conducting bar. So here I am considering a conducting bar like this. Right. Okay. So now see here. Now if I move this conducting bar here, see initially this is the area. This is the area enclosed by this loop here. Yes or no? This is the area enclosed by this loop. Understood? So now what I am doing here is I am moving this conductor towards right with some velocity v. Understood? So whenever, let us assume a kid here, kid is playing with this conducting bar. So he is trying to move this conducting bar. He is trying to move this conducting bar towards right here, towards right. Understood? Okay. So let us assume these two are conducting rails which are frictionless here, frictionless. So that means you can move it freely in rightward direction. So let us assume a kid is moving this conducting bar in rightward direction like this. Okay, so whenever he is moving this conducting bar in rightward direction like this, so then what will happen here? The area of the loop enclosed, what I am saying here? Okay, so as this conducting bar moves here, as this conducting bar moves towards right, so then what will happen here? The area of the loop is going to what? Is going to increase or not? Yes or no? It is going to increase with respect to time. So as the area of the loop increases with respect to time, what will happen here? What will happen? The magnetic flux will also increases with respect to time or not? Yes or no? See, let us say this is at t equal to 0 instant. So after some t equal to 1 second or something, or t equal to 1 millisecond or something, let us assume this has moved from, this is position 1 to what? To position 2. Understood? So whenever it is at position 1, this is the area it is enclosing. Now whenever it is moved to position 2, then this is the total area. Yes or no? This is the area enclosed by what? Enclosed by this loop. Understood? So as it moves further, what will happen here? The area enclosed by the loop is going to change. Understood? So as the area enclosed by the loop changes, what will happen? The number of field lines that are penetrating through this surface is also gradually increasing or not? So that means the magnetic flux is increasing. Understood? So whenever the magnetic flux is increasing, okay, we know that that means magnetic flux is increasing means magnetic flux is changing. So whenever there is a change in magnetic flux, what will happen? We know that there induces an EMF around the closed loop, which is going to drive the induced current. Understood? And hence you are going to see what? You are going to see this bulb glow. You will see this bulb glow. Understood? Okay. Okay, so once he stops moving here, once we stop moving this conducting bar, then bulb will not glow, right? See, next again in the same manner, if you move the conducting bar to leftward direction here, so then what will happen here? In this case, the area enclosed by the loop will gradually what? Will gradually decreases. So as the area decreases, what will happen here? The magnetic flux through that surface area will also what? Will also decreases with respect to time. Understood? So in that case also you will see the bulb glowing. Understood? Yes or no? Because in this case also the magnetic flux is changing. So if you don't move the conducting bar, then you are not going to see any glow of the bulb. Okay, so whether it moves in this direction or in this direction, in both the cases there is a change in magnetic flux and hence there induces an EMF, and hence you are going to see some induced currents, and hence this bulb will glow. Understood? Okay, so this is another way to produce what? To produce an EMF. Understood? Okay. So next coming to this one, how we can produce an EMF by varying what? By varying theta with respect to time. So this is what we are going to see now. Right? Okay. So I will copy this one here. Okay, otherwise I will explain here itself, okay, so that everything will be present here, right? Okay, so consider this one here, So here we are producing the EMF by varying what? By varying theta. So theta is the angle between what? Between B field and area vector. Yes or no? It is the angle between the B bar and A bar. B bar and A bar. Remember that. Okay. So see, now I will explain how we can produce an EMF by varying theta with respect to time. Okay. See here, let us assume here you are having a north pole here, and here let us consider south pole. So I have placed a magnet here, right? Okay. So the magnetic field lines will point from north pole to south pole, in this manner, right? Okay. So now here let us consider I have placed a conducting loop here. I have placed a conducting loop in this magnetic field. Understood? Okay. So let us assume I am rotating this conducting loop here. Okay. Let us say it is rotating like this. Understood? So the conducting loop is rotating in the magnetic field. So in this case, what is changing here? See, this B field is not varying with respect to time. See, the magnitude of area of the loop is also not varying with respect to time. So what is varying with respect to time here? Whenever you are rotating this conducting loop in the magnetic field, what is going to vary? Tell me. See here, let us assume initially, so let us consider this is loop here. This is loop. Understood? Okay. So now here the B field is pointing like this. Okay. So the loop is this one here. So this loop is enclosing this surface area. Right. Okay. So what is the direction of the surface area here? So let us consider, always the direction of the surface area is given by the unit normal drawn to that surface. So let us assume the direction of this surface area is pointing in this direction. Okay, in this direction. Right. Okay. So now the B field is also pointing in the same direction. So now in this case, theta is equal to what here? Theta is equal to 0 degrees. That means the angle between B field and the area vector, both are what? The angle between B field and area vector is what? Is 0 degrees. Understood? Okay. So in this case, when theta equal to 0 degrees, you are going to see what? Maximum flux through the surface. Yes or no? Okay. So now as you move this conducting loop here, like this. Understood? So as you go on move this conducting loop like this, then what will happen here? The number of field lines that are penetrating through this loop will gradually what? Will gradually decreases and becomes what? Now it becomes 0. Yes or no? Now what is the angle here? What is the angle between B field and area vector here? So B field is pointing in this direction, area vector is pointing in this direction. Understood? So that means here the theta will become what? Theta is 90 degrees. So whenever theta is 90 degrees, in that case there will be no flux through what? Through the loop. Understood? So initially it is like this. So here theta equal to 0 degrees. So as I move this conducting loop like this, theta is changing, and hence the magnetic flux through the loop is also decreasing. Now theta becomes 90. Now in this case the magnetic flux through the loop will become what? Will become 0. Yes or no? Next again theta is changing, and the magnetic flux through the loop is also increasing and becomes maximum, and again it decreases and becomes 0. Yes or no? So like this here. So as you rotate this conducting loop, in the magnetic field, what is changing? Theta is changing. The angle between B field and area vector is changing with respect to time. Here B field is constant with respect to time, and area of the loop, the magnitude of area of the loop is not changing with respect to time. Understood? What is changing? Only theta is changing with respect to time. So whenever theta is changing with respect to time, what is happening? There is a change in magnetic flux or not? Yes or no? So the number of field lines that are penetrating through this loop is changing with respect to time as theta changes. Understood? Okay. So by rotating this conducting loop in the magnetic field, what is going to change? Theta is going to change. With respect to time. So if theta changes with respect to time, so then also there will be a change in magnetic flux, and because of this change in magnetic flux, you are going to have what? You are going to have an induced EMF. Understood? Okay. See, I will explain this rotation of the loop in magnetic field, all these things in a detailed manner later. As we proceed into the subject, I will explain this in detailed manner, right? Okay. So this is the basic principle here. This is the basic principle that you will use in generators. Yes or no? Okay. So in AC generator, and also this is the same principle you are going to use in DC generator also. Yes or no? Okay. Okay. Yeah. But the way you are going to connect these endings will be different in AC generator and DC generator. Okay. So we will see here. We will see briefly those things as we proceed into the subject. But as of now, just consider that whenever this conducting loop rotates in the magnetic field, theta is going to change. Whenever theta is changing, the magnetic flux is changing. Whenever the magnetic flux changes, there induces an EMF around the closed loop. Understood? Okay. So this is what you have to understand. Right. Now here we have produced the induced EMF by what? By rotating the conducting loop in the B field. By rotating the conducting loop in the B field. So we call this as what here? We call this as a rotational action. Rotational action. And the EMF that we produced here, we call it as what? We call it as a rotational EMF. We call it as what here? Rotational EMF. Understood? Okay. Now what is the name that we can give for this one here? See here, by moving the conducting bar either towards right or towards left, we are producing what? We are producing the EMF. Understood? So here, through the motion of this conducting bar, we are able to produce what? We are able to produce the EMF. So that's why we can call it as what here? We can call it as a motional EMF. We can call it as motional EMF. Okay. See, in generally we can call it as rotational EMF, or since it is also through the motion of the conducting loop we are producing the EMF, and hence this one also is called as what? Rotational EMF, or sometimes we can call this also as what? We can call this as also motional EMF. So specifically speaking, we will say it as rotational EMF. Generally speaking, we can say it as motional EMF also. Understood? Okay. So through the motion of the conducting loop here, and here through the motion of the conducting bar. So that's why this EMF we call it as what here? In general both can be called as motional EMF. So specifically this way of producing EMF, specifically we call it as rotational EMF. Understood? Okay. Okay. So these are the different ways. Through which we can produce what? We can produce the voltage. Understood? Okay. See here, in previous gate questions they have asked one simple question here. So you have to tell the answer here. I will give that question. Right? Okay. So these are the different ways through which we can produce what? We can produce the EMF. So one is by varying the B field with respect to time, and another one is by varying the area of the loop with respect to time, or by rotating what? By rotating the conducting loop in the B field. So these are the different ways through which we can generate what? We can generate the EMF. Right? Okay. Okay. So what is the question they have asked in gate previously is a direct question they have asked here. See here. What they have given here is they have given that B field. I am not writing the total question here, just I am giving that idea what they have given. So they have given B field. As B bar is equal to B naught into cos of omega t plus phi. Understood? Okay. Cos of omega t plus phi. Right? So omega t plus phi ax cap. So now they have given a conducting loop. Is rotated, or you can say a conducting loop is revolving about y-axis in the given B field, right? So this is the given B field here. So given B field is this one. B bar is equal to B naught into cos of omega t plus phi Ax cap. So they have given that a conducting loop is revolving about y-axis in the given B field, So that means, see here, so this is, let us say this is or there is no need here. Okay, so let us say this is the conducting loop, right? Okay, so let us consider this is y-axis, here. Let us consider this is y-axis. So this loop is rotating about what? About y-axis. This loop is rotating about y-axis. So the B field is pointing in which direction? The B field is pointing in Ax cap direction. So let us consider this axis here. Let us consider this axis as x-axis, right? Okay, so that means here the B field is pointing. In which direction? They have given that the B field is pointing in x direction. Understood? And if you observe, this B field is varying with respect to what? This B field is varying with respect to time. Yes or no? So this B field is varying with respect to what? With respect to time. Okay, so now they have given options here. They have given the options like the EMF induced in the loop is due to transformer action, is due to rotational action, is due to both transformer action as well as rotational action. Okay, so these are the different options they have given, right? Okay, so through which action we are generating the EMF in this case? Tell me, through which action we are generating the EMF? See here the B field is varying with respect to what? B field is varying with respect to time. Yes or no? So if B field is varying with respect to time, then that action of producing EMF is called as what? Is called as transformer action. Yes or no? Okay. Next, in this time varying magnetic field, here the loop is revolving about what? About the y-axis. That means here the conducting loop is rotating in B field. So whenever the conducting loop is rotating in B field, what is going to change here? Theta is going to change. That is the angle between B field and area vector is going to change. So that means here, if theta is changing here, then that action we call it as what here? Rotational action, or we can say it as what? Rotational EMF. Understood? Okay, so that means here in this case they have given both B field is varying as well as what? As well as theta is also what? As well as theta is also varying with respect to time. Understood? And hence here the EMF, in this case EMF produced is due to what? Is due to both what? Both transformer action as well as what? As well as rotational action. Understood? Okay, so EMF produced in this case is due to both transformer action as well as what? Rotational action. So this question is given in previous year gate. Okay. So this is a direct question here. You can easily answer this one. So if you understand this concept, then you can easily answer this type of questions here, right? Okay. Right. Okay. So now so we try to solve one problem here. Right? Okay. So write down your problem here. So a circular loop of wire A circular loop of wire of radius a. A circular loop of wire of radius a is placed in a uniform magnetic field. See, uniform magnetic field means it is not going to vary with respect to time here. It is not going to vary with respect to time. So if the magnetic field is constant with respect to space, we call it as what? We call it as generally uniform magnetic field. Understood? Okay. So a circular loop of wire of radius a is placed in a uniform magnetic field. Right. With the plane of the loop perpendicular to the direction of the field. Direction of the field as shown in figure. So here they have given this figure here. So here they have given that the B field is pointing, this uniform B field is pointing into the board. Right. So this is the circular loop. So its radius is how much here? The radius of this circular loop they have given as a. Right. Okay. So this is the figure. They have given. So B field is pointing into the board, and this is the loop of radius what? Of radius a. So the plane of the loop is perpendicular to what? Is perpendicular to the field. Okay. Okay. So here the B field varies with respect to time. According to B of t is equal to 5 plus 2t. Okay. 5 plus 2t. So in option A, in A, they have given that they are asking that calculate the magnetic flux. Calculate the magnetic flux at t is equal to 0. At t equal to 0 second. Next, in B, calculate the induced EMF in the loop. Calculate the induced EMF in the loop. Okay. Next, here write down one more thing as shown in figure, right? Okay. So here write down the overall resistance. The overall resistance of the loop. The overall resistance of the loop is R equal to 10 ohms. R equal to 10 ohms. Right. Okay. So calculate the induced EMF in the loop. Next, C. What is the induced current? What is the induced current and its direction? What is the induced current and its direction? Next, D. find the power dissipated due to the resistance of the loop, due to the resistance of the loop. Okay. So see here, so here what they have given here, a circular loop of wire of radius A. So let us consider, let us take some value for A here. So let us consider radius A is equal to 1 centimeter. Let us consider A is equal to 1 centimeter here, right? Okay. So here let us consider A is equal to 1 centimeter. Okay. So a circular loop of wire of radius A is equal to 1 centimeter is placed in a uniform magnetic field with the plane of the loop perpendicular to what? Perpendicular to the direction of the field as shown in figure. Right? Okay, as shown in figure. So the overall resistance of the loop is how much here? R equal to what? R equal to 10 ohms. The B field varies with respect to time according to B of t is equal to what? 5 plus 2t. So you have to determine what here? You have to determine the magnetic flux at t equal to 0 seconds. So first we try to determine A. So next what they are asking, calculate the induced EMF in the loop. Next what they are asking, what is the induced current and its direction. So next what they are asking, find the power dissipated due to the resistance of the loop. Understood? So these are the 4 things we have to determine, right? Okay. So now see here. Right. Okay. So here A is equal to 1 centimeter, resistance of the loop is equal to 10 ohms, and B of t is equal to what? 5 plus 2t. So these are the things they have given, right? Okay. So first one we try to determine. So what is the first one here? They are asking, calculate the magnetic flux. Calculate the magnetic flux at t equal to 0. At t equal to 0. See, what do you mean by magnetic flux here? What do you mean by magnetic flux? So the number of field lines that are penetrating through this what? That are penetrating through this loop. Yes or no? That is nothing but magnetic flux. So we know that how to calculate the magnetic flux. So that is nothing but phi b is equal to what? Phi b is equal to, I can write directly b bar dot what? B bar dot a bar. B bar dot a bar. So why I am writing b bar dot a bar here? Because they have given that B field is what? B field is uniform. So whenever the B field is uniform, or if it is constant with respect to space, then you can directly write it as what here? B bar dot a bar. So I have already explained this thing here, right? Okay. So you can directly write it as B bar dot a bar. Now here, let us assume here, okay. So assume the direction of area is pointing out of the board. Let us assume. Okay, so assume the direction of area is pointing out of the board. So that means the area direction must be, you have to take out of the board here. You have to take out of the board, right? Okay. Okay. So now see here. So B bar dot A bar is equal to what? Is equal to B into A into cos theta, where theta is the angle between what? Where theta is the angle between B field and area vector. So here they have given that area direction is pointing out of the board. That means it is pointing out of the board, and B field is pointing into the board. So that means here theta is how much here? Theta is 180 degrees. Theta is 180 degrees. Yes or no? Okay. Okay. Please include this one in the problem itself here. Assume the direction of the area is pointing out of the board. Okay. So first we will try to solve this type of problems, right? So later I will explain in general. How to consider the direction of area and all those things, right? Okay. So as of now, continue in this manner. So theta is 180 degrees here. So if theta is 180 degrees, so then cos 180 is what? Minus 1. So that is, you are going to get what? You are going to get minus b into a, minus b into a. So that is equal to what? That is equal to minus of minus of b. What is what they have given here? 5 plus 2t. Yes or no? 5 plus 2t into area of the loop, into area of the loop. What is the area of the loop here? Area of the loop is nothing but what? Pi into a square, pi into a square. Yes or no? Okay, so that is equal to minus of 5 plus 2t into what? Into pi into a is how much here? 1 centimeter. So that means 10 power minus 2 whole square, that is 10 to the power of minus 4. Right? Okay. Okay. So this is the magnetic flux here. This is the expression of magnetic flux we got. This is the expression of magnetic flux we got. So they are asking the magnetic flux at t is equal to 0. Yes or no? So therefore at t is equal to 0 here. At t is equal to 0, what is the magnetic flux you are going to get? Tell me. At t is equal to 0, what is the magnetic flux you are going to get? So substitute t equal to 0 here. What you are going to get? Minus 5 pi into what? Into 10 to the power of minus 4. Right? Okay, so minus 5 pi into 10 to the power of what? 10 to the power of minus 4. So what are the units of magnetic flux? Is nothing but Weber. Right? Okay. Okay. So for B field it is Weber per meter square. For area vector it is meter square. So the units of magnetic flux is nothing but what? Weber. Right? What here? Okay. So A is completed here. So next B, what they are asking here? Calculate the induced EMF in the loop. Calculate the induced EMF in the loop. See how to calculate the induced EMF here? We know that from Faraday's law, the induced EMF in the loop is equal to what? Is equal to minus dou phi b by what? Minus dou phi b by dou t. Understood? So just substitute this magnetic flux here. Understood? So this is equal to what? This is equal to minus dou by dou t into phi b is how much here? Minus of 5 plus 2t. 5 plus 2t into what? Pi into 10 to the power of minus 4. Right? Okay. So if you do this differentiation, what you are going to get? Here minus will become what? Plus. So here you will get 2 pi into what? Into 10 to the power of minus 4. Right? Yes. Right? Okay. So 2 pi into 10 to the power of minus 4. So this is what you are going to get. So 2 pi into 10 to the power of minus 4 volts. Okay. So this is V EMF here. Okay. So next, that is the induced EMF. Next here. So next, what they are asking? What is the induced current? What is the induced current and its direction? What is the induced current and its direction? So that is C here, C. Okay. So here I am doing here C. What is the induced current here? If you want induced current, what you have to do? V induced EMF divided by what? Divided by, they have given the resistance of the loop. What is the resistance of the loop? That is nothing but R. Yes or no? So V EMF is equal to how much here? 2 pi into what? 2 pi into 10 to the power of minus 4 divided by what? Divided by R. R is how much here? 10 ohms. So you are going to get what? You are going to get 2 pi into 10 to the power of minus 3 amperes. 2 pi into 10 to the power of minus 3 amperes. Now we have to determine the direction of the induced current. The direction of the induced current. So in which direction the induced current will be? Tell me. In which direction the induced current will be? Tell me here. See here, if you observe the B field here, if you observe the B field, they have given that 5 plus 2 times of t, 5 plus 2 times of t. So that means as t goes on, increases here. So with respect to time, this B field will also going to increase. Yes or no? This B field is going to increase with respect to time. So the B field is pointing into the board and it is increasing with respect to what? With respect to time. So that means the magnetic flux into the board is going to increase with respect to what? With respect to time. So we know that whenever the magnetic flux is increasing with respect to time here, whenever the magnetic flux is increasing with respect to time, then what will happen here? The induced magnetic field direction, the induced magnetic field direction must be exactly opposite to what? The direction of the actual magnetic field. So now here the actual magnetic field direction is pointing into the board. So that means the induced magnetic field direction must be what? Must point out of the board. So if the induced magnetic field is pointing out of the board, means the induced current must flow in which direction? In anti-clockwise direction, like this. Yes or no? Okay. So that means in this case the direction of the induced current here, the direction of the induced current must be in anti-clockwise direction, like this. Okay. Okay. So the direction of the induced current. So you can draw simply loop here. So the direction of the induced current will be what? Will be in anti-clockwise direction, like this. Right? Okay. So we have determined the induced current value and also we have determined its direction, right? Next what they are asking here? Next they are asking, find the power dissipated due to what? Due to the resistance of the loop. So they are asking to determine what? To determine the power, that is dissipated due to what? Due to the resistance of the loop. So what is the power dissipated here? How to determine the power dissipated? We know that power dissipated in the loop, is equal to what? Is equal to, I can write V EMF square divided by what? Divided by R. V EMF square by R. Okay. So what we can, or you can write I induced square into R. So anyway you can determine here. So this is the V EMF value, 2 pi into 10 to the power of minus 4. So that is equal to 2 pi into 10 to the power of minus 4 whole square divided by what? Divided by 10. Understood? Okay. So this is what you are going to get here. This is what you are going to get, right? Okay. You can calculate this one here. You can calculate this one. So this is the power dissipated in the loop. Power dissipated in the loop, right? Okay. See, the problems are very, very simple, right? Okay. So first we will start with simple problems. So then we will increase the difficulty level. Okay. Okay. Right. Okay. So next next here I will give you one problem here as homework. So I will give you one problem as homework, right? Okay. So you can try this one. So here let us consider a closed loop. Here the B field is pointing into the board. Okay, so this is B field. So here this B field is given by B of t is equal to 5 into cos of 2 pi into 50 into t. Okay, into t. It is pointing into the board. Okay, so Weber per meter square, Weber per meter square. So this is the B field. This is the B field. Okay, so now the B field I have given as what here? A sinusoidal variation, right? Okay. Okay, so let us consider this as a 3 centimeter and this as a 10 centimeter. Okay, so this length is 10 centimeter and this breadth is 3 centimeter, right? Okay. Okay, so here assume the direction of the surface, is pointing is pointing out of the board, is pointing out of the board. Okay. Okay. So for this problem, calculate this A, B, C, D here, whatever we have done in this problem, okay, so that is A, B, C, D. So all these things here, all these things try to calculate here. Okay, so for this problem try to calculate all these things. So that is calculate the magnetic flux at t equal to 0 seconds. Next, calculate the induced EMF in the loop, what is the induced current and its direction, and find the power dissipated due to the resistance of the loop. So let us consider the resistance of this loop here. Okay. So resistance of the loop is equal to 5 ohms. Let us consider the resistance of the loop is equal to 5 ohms, right? Okay, so this is the data I have given here. So try to determine all these things here, A, B, C and D, right? Okay, so do this as homework here, do this as homework. Okay. Okay. So with this I am winding up the session here for today, right? Okay. Okay. So with this I am winding up the session for today. So tomorrow exactly at 4 p.m. we will meet here, right? Okay. So until then, stay safe and keep learning, right? Okay. Okay, so we'll meet exactly at 4 p.m. tomorrow. So until then, stay safe and keep learning, right? Okay. So okay then, take care, bye bye.